All right, without further ado, let's get started. Again, welcome back. Folks, I know that several of you send me emails. I hope I responded to almost all of them except a few. I'll make sure I've received your emails. I'll make sure to respond to it by the end of today. All right. Sorry, I've not been doing too well with some medical conditions. So if you have any other questions or comments, don't hesitate to come to my office after class today. And I'm going to post, I finally got all the schedule from all the TAs, and I'm going to post it. Like I will work on it after class today. All right. Any other questions based on what we covered so far? We didn't cover anything technical per se. We mostly covered motivational stuff, but in case you're curious. All right. If not, we can get started today. So we'll do a quick review, like super fast, quick review of number systems and Boolean algebra, right? As you can tell, this course is heavily reliant on, these two topics, number systems and Boolean algebra. And I already indicated that there is one particular number system that we'll be using for digital electronics, and that is binary. But that doesn't mean you don't care about the others. And I'll probably give you some hint as to how they can be useful, even for digital electronics. So let's start with some very brief history. And when I say brief, it's actually really, really brief. All right. So don't worry about this taking up too much time. This is how the journey began. And the reason for these slides is to show you that it didn't really happen overnight. All right. It escalated over the last couple of decades in terms of, surge in capability. But the, sowing the seed to developing concepts to having the big impacts, they date back centuries, actually. And I'm not kidding, honestly. As you see, it started in 19th century when people started at least trying to make devices that could compute, right? And remember, the first few computers, most of the computers were all analog, okay? And they had some specific purposes, like, for example, predicting tide. That was necessary at the time. Now you can use an app to do so. But at the time, just calculating maybe the position of the sun and maybe coming up with a calendar that, you don't have to make a Stonehenge, for example, to keep track of time. A device that could do so was extremely valuable. And as you can tell, they were all like custom designed and custom made. And there are like a few of them in the world available, probably within the royalty per se. So it was not available to mass population, as you can imagine, right? So they're extremely expensive, extremely rare. Every once in a while, there was a feature. Do any of you read IEEE Spectrum? No, it's a magazine. Great. If you are IEEE student members, you should be able to get access to this. This is interesting. They have features about all types of IEEE related stuff. And there was a feature recently, you can Google it. You don't have to be a member of IEEE, just Google it. There was an analog calculator that they found in a shipwreck, right? Like a shipwreck centuries ago, for example. And they found a device that they couldn't make sense of. And apparently somebody realized by reverse, designing with 3D mapping and everything, that it is essentially a calculator. It was a really nice, sophisticated calculator. And they were surprised. We have no background knowledge of how that calculator came into being. Does that make sense? So just imagine that. So why am I telling you this? This is one of the more structured and documented way of making computing devices by Charles Babbage, who created a device called difference engine in 1820s, as you can see. Important point here, it was a mechanical computer. And most of these computers were mechanical computers because we didn't have any electrical concept at the time. Electronics, forget about electronics, not even electrical activities, not, at least not to that degree. And then Auguste King put forth the concept of programming, or basically she described an algorithm for machines like the difference engine that Charles Babbage developed. So apparently, if you have hardware which can possibly do computing, there should be a way to program those hardware in a certain way. All right. So like the way we do for our computers today, which is 100% electronic. At the time, this was the first ever attempt to program a computer, but obviously it was a mechanical computer. It's nothing similar to what we are dealing with today. Now, as we move forward in history, the importance of calculating machines was becoming apparent, and for many reasons, ranging from war to predicting, crop yield to ship navigation, you name it. So there were specific needs to specific people who could have, enough money to and time and skill to spend on it. So it was like very limited niche. Fast forward to 1840s, and I just want you to pay attention to how, all these concepts are and these developments were. 1840s, almost 200 years ago, for example, right? George Bull, I mean, I hope you can make the connection, Boolean algebra. So it comes from his name. Something that we are using to this day, literally. There is no digital electronics without Boolean algebra. And this guy, he came up with the concept. He was a self-taught math. If you're interested, read through this. I mean, I don't want to read the entire thing. These are all taken from internet, obviously. And by the way, many of these slides were adopted from Professor Rose, who taught this course before. So I make sure that I cover everything that he covered, and then maybe I add a few other concepts, all right? So many of them, I have to acknowledge his kind support in helping basically prepare the slides. So George Bull, he was basically, now we have everything structured. You are an electrical engineer, mechanical engineer, nuclear engineer, blah, blah, blah. We have everything structured. Here is what you need to do to get a PhD, to get a master's. At the time, knowledge was like, there was no such solid structure per se. So you could have an interest and you end up becoming very famous without going through a formal channel of education, getting all the degrees and, you know what I mean, right? So similar to that, he was a self-taught logician. I mean, do you know of anybody today who basically identifies themselves as, what do you do? I'm a logician. I don't think so, right? So basically, he used to think of logic. It's basically close to philosophy. He was not, honestly, he was not really an engineer per se. He was more like a philosopher. So modern philosopher, not like, get Archimedes, for example. Not that way, but to some degree, he used to think about logic. And in doing so, he came up with the concept. He basically tried to define and describe logic using mathematics, right? Like, for example, logic could have two solutions. Something could either be true or false. And he didn't have anything in between. It's either true or false. Does that make sense? And the same concept that he thought about almost 200 years ago is still being used today, because when something has two values, true or false, it could also be treated as high and low or on and off. Basically, that is the whole point of binary. But at the time, nobody made that connection because there was no concept of, say, binary at the time, right? But he introduced the concept of Boolean logic. So basically, he found a way to connect logical decisions with mathematics. That's all. Okay. I'll talk about some of this logic, like and, or, XOR, and whatnot, moving forward in this slide, in this lecture particularly. But just to give you an example, when we talk about logic, with our fellow peers, we don't necessarily think about it in a mathematical way, right? We just, hey, that's not logical. What you're telling me is not logical. How do you know? How did you decide? Did you use any algorithm to decide that your friend was telling you illogical stuff? No, we don't do that. But honestly, in our head, maybe somehow there is a circuit that does it. But you cannot have a machine do that emotionally. Like, hey, I don't think it's logical. Why? Because I went through such and such steps and my output is 0, which shows false. So I think it's not logical, something like that. So you have to find a way to define or describe how we reason, how we find something logical. And that's exactly, I mean, if I'm sounding like a philosopher, that's exactly what he was, as you can see, right? He was trying to, how do we decide on something in a structured way, setting aside the emotion? And that was behind the concept of Boolean algebra. He basically defined or described logical decision using algebra. And we'll see some of this today. And that was the reason I'm stressing it so much, is because this is basically the foundation, remains the foundation of digital electronics today, all right? De Morgan, get used to, basically, we have to acknowledge, he became a great collaborator of Boole, but at the time, just imagine you are a couple of guys thinking of defining logic with mathematics. How many other people will care about it, right? Not too many. So the fact that at the time you had the, per se, audacity to spend your own time collaborating with someone and coming up with ideas. Basically, De Morgan's law is one of the foundational concepts that we still use to this day. And you'll see it, I mean, we'll probably not realize the impact of it in this course, but I'll try to connect it to something bigger, honestly. I'll try. I don't know whether you'll see that, but honestly, the final connection will be clear if you take 651, which is computer-aided design of VLSI system, which is like the very high level course. That's when you see how we use this De Morgan's law to simplify and automate the design of logic gates. Obviously, as you can imagine, if there are billions of something, whatever it is, transistors or whatever, you cannot manually design all billions of them, and you cannot manually connect. There has to be a structure and algorithm that automates the design process. Okay, it is literally called design automation. To be exact, EDA. This is a very big multi-billion-dollar field in electronics. Electronic design automation, and the foundation of design automation relies on, among other things, one of the foundational concepts is De Morgan's law. Yes.
So is De Morgan's laws like, is that a blueprint to how everything that small should be designed, or is it the actual structure of the, I don't know if you understand.
That's a great question. First of all, it is not related to things being small. That is a completely different strategy that basically arose from, you remember Gordon Moore, Intel's co-founder, his prediction. And he wanted to have basically double the number of transistors every 2 years. And to achieve so, you needed to make things small. And along the way, we realized when you make things small, you get some additional benefit. And further down the line, we realized, oh, yes, you do get some benefits, but you do also have some challenges. So, right? That's more like a side or byproduct of scaling, but it has nothing to do with scaling. Doesn't matter which scale you're dealing with. If it is a small transistor of today's technology or bigger transistor 50 years ago, we always used this law. You know, this is so ubiquitous, actually. And honestly, it will be clear. So basically, this has to deal with making Boolean logic design universal. I know it's a lot of empty words right now, but trust me, as we go through this course, it will be clear. And I will try to connect it back to this point. Hey, remember I told you that De Morgan's law had a big place. So that's the reason why he's here in our slide. Does that make sense? And by the way, after a while, after we go through a few discussions of this law and others, if it doesn't make sense, please make sure to put the question back and ask me again. All right. So by the way, you see that mentioned here. This law will play an important role in optimizing digital logic circuits. All right. And we'll get to that because we don't know how to optimize digital logic circuits. So how will you know how to use this law? All right. Now, at the 20th century, the ideas of logicians were important to philosophers, blah, blah, blah. Just read it at home. I just want to highlight another foundational contribution from Vannevar Bush in 1920s. And he constructed a computing machine called differential analyzer. Okay, this is also like, it's not a digital computer or anything like that. The unique part, the reason why it is so unique was because this was an electronic system. Okay, it's not like Babbage's engine, which was fully mechanical. This was an electronic engine. So this was a very big step. How do you transfer your computing machines completely from mechanical domain to an electronic domain for the first time ever? So that was a very big deal. And there is another reason why he's famous. How many of you have heard about National Science Foundation, NSF? Right? This is basically almost like the driving force behind US science. And there are other entities that are similar to NSF from other countries. Canada has it. Singapore has it. Europe has their own entity that resembles NSF. But NSF was basically the foundation of structured science and engineering efforts in the US. So this is a very big impact. Obviously, it's not directly related to digital electronics, but I think this is probably the biggest step ever towards. This is the last history slide. Don't worry. As you see, after that, we don't have any more history. These are only select few people. Obviously, it cannot just happen with like 4 or 5 people, right? There are hundreds of people who contributed, obviously. But these are so impactful that we have to have them in the slide before we even begin discussing digital electronics. So Shannon, he's an American mathematician. Forgot to mention Babbage. They were like British. In late 1930s, he was a student of Vannevar Bush at MIT. And his master's thesis first introduced the concept of how to use switching circuits. So something that switches between one phase to the other, or one state to the other. And how to use these circuits to represent Boolean logic. Does that make sense? Do you see the connection? Boolean logic, which was introduced in 1940s or so, 100 years before, it literally took 100 years, 1930s, for someone to figure out a way to use electronic circuits to represent Boolean logic. So Boolean algebra was already in place. Somebody, like as you can see, Bull, he already described how you can use mathematics without like using emotion to make logic, right? How can you use mathematics to come up with logical conclusions? So he already did the math, but nobody knew how to use it. Just imagine you being a person in 1900s even, say 1890, 1900s, you know, somebody worked on a mathematics that describes logic. How do you use it? There was absolutely no use case, like nothing. You have no use for that. Okay, are you gonna use this logic to make life decisions? Let's see, A XOR B, then, okay, if this happens, then I'll buy a car. There was absolutely no use case if you think about it. But 100 years down the line, somebody connected this math. We could represent this mathematical expressions using circuits that switch. And then it automates the logic process, which is basically the building blocks of computers. Computers, all they do is they deal with logic. Does that make sense? So that's how impactful a discovery can be. Obviously, it may or may not materialize within our lifetime, but if you do something foundationally unique, at some point it will probably pay off. Okay, so long story short, I hope that was a quick. Please feel free to Google and do Wikipedia search or ChatGPT search about them and learn about other fascinating stuff. I want to highlight one before I move over to number systems. Obviously, it's a very quick review. I know how many of you have taken courses or have background on binary, hexadecimal. Almost all of you, obviously. So it will be just a couple of slides. No worries. So it's not going to be a super long review. Just a reminder, okay? Okay, and I just want to sneak this slide in to show you. This is basically me getting ahead of ourselves. This is way down the line. This is a slide that I use in 433, where you basically design circuits, specific circuits to represent logic, right? Okay, so, but why am I showing you this? So that you can relate. Now, I'm looking for something. Every once in a while, I have this empty slide where I can draw. So I'm going to draw something. Take a look at a transistor. This is not a transistor course, but it will take me like 2 minutes to explain it. It has 3 terminals. You have gate, you have drain, and you have source. Okay. When you apply for a particular type of transistor, which is NMOS, if you apply positive voltage to the gate, it creates a channel, and you can conduct electricity through that channel. All right. If you provide 0 voltage to the gate, it disrupts the channel. So there is no longer any other channel. So then electricity stops. Okay. So basically, can I say that when you have positive voltage to the gate, it's like a switch being closed. If you have 0 voltage to the gate, it's like a switch being open. Can I say that? So I can use a transistor literally to represent, say, this is 0, this is 1. Switch off, switch on. So simple. You can use voltages to turn on or turn off a transistor. Okay, now heading back. Use our conventional common sense. Say an event will occur if A and B both take place. Does that make sense? Say when you get into a car, when you put your car on drive and close the door, only then the lights will close and it will be ready for. So 2 events has to occur, or maybe multiple, A and B and C and D. multiple events have to occur. Only then you have a certain output, right? That's an AND relation. That's something called AND. So notice, this is the logic. If A and B occurs, then your output should be 1, meaning output should be activated or something like that. You could always represent it as activated, deactivated, true, false, high, low, whatever you want to call it, like 2 stages. Now, notice, I'm going to draw something here, a transistor, another transistor. Notice, A and B could be used as inputs. Okay? Imagine I represent event A as a voltage and event B as another voltage. Okay? So if when you close your door, a voltage goes up. When you buckle your, belt, seat belt, another voltage goes up. So A going up, meaning 1. B going up, meaning 1. Am I making any sense at all? So that's why I'm struggling. But hopefully it will be okay. So when I say 1, a voltage going up, it's probably a positive voltage. Similar, a positive voltage at the B. That means both of these transistors will be on. Can I say that? Okay, these are series connected transistors. And I know you guys have ideas about series and parallel. Imagine if I have VDD, which is a high voltage. In circuit, we represent high voltage or high logic with VDD and low with 0, ground. When you connect ground, it represents 0 logic. When you connect VDD or supply voltage, whatever that might be, your VDD could be 2 volt, 5 volt, doesn't matter. Whatever is VDD is represented as logic 1. And whatever is ground or 0 is represented as 0, as the name suggests. All right. Okay. Now, if I apply VDD here, this is your output. Your output will only be VDD when both of these transistors are on. Can I say that? Can I say that? Can I write your output will be 1 when A equals 1 and B equals 1? Can I write that? Okay, I'm going to write this as a function, if. So I'm going to make a table here, if. So when A and B both are 1, your function will be 1. Let's do a different trick here. If one of them is set to 0, say B didn't occur, is it too busy? If you pay attention, it will be okay. Otherwise, it's getting messier. Are you still with me, folks? If one of these events didn't occur, say B didn't occur, like B is 0, then what? Then will there be any direct conduction from this node to the other node? No, it will be cut off. So our output could be 0. So if either B is 0, A 1, or A is 0, B 1, your output will always be 0. Does that make sense to you? And if both of these are 0, obviously, there is no chance your output will be VDD. It's definitely going to be 0. So what you're looking at here, this is what I just made, is called a truth table. This basically comprises all the possible combinations of A and B, which are our inputs. Does that make sense? Okay. So notice, I have basically represented a logic truth table using 2 series connected transistors. There you go. It's an AND gate. Okay, that's how you do it. I just wanted to get ahead of myself and really show you what it means when Shannon found a way to represent logic with circuits. This is what it means. All right. Okay. At the time when Boolean algebra was introduced, transistors didn't even exist. Nobody knew. And by the way, Shannon didn't have to use transistors to make the circuit. This was not even discovered at the time when he proposed. He used other kind of switching devices, by the way. Transistor is one type of switching device, but there are other switching devices that people used in the past. All right. So I'm not getting into that history. All right. So by the way, just to also show you, let's see, can we do a quick exercise here? And this could be interesting opportunities for extra credit, right? Somebody asked about extra credit, right? I'm not doing it today. It's very new for most of you. I don't want to put you at a disadvantage, but every once in a while in class, I can give you a question And if you can answer, you might get some extra credit. You never know, right? So this could be one of the extra credit questions. What if I want to add an extra input? I don't want to do a 2-input AND. I want to do a 3-input AND. Meaning, if you close the car door and buckle your seatbelt and then put your car on drive, only then something will activate. Something. Maybe your navigation will show up, right? So you need 3 events, A, B, and C. How can I change this circuit to incorporate that extra event? C. Yes. Okay. Thank you. Good try. Why parallel? Why parallel?
They're like next to each other or separate?
So I have 2 transistors in series right now. So the third one will be in parallel to the connection that I have or no? No. Think about it a little bit. You're heading the right direction. Yes. Go ahead.
You put another one in series.
Yes. Thank you. I guess. Yeah. So thank you for trying, all of you. And like I said, this could be an interesting extra credit. Why? Because remember, all 3 of these events have to occur together to have a final output, right? So if you, here is the problem if you put it in series. Let me show you. 2 transistors. Now imagine if you have another transistor in parallel. Now, this is A, B, and C. If A and B both are 1, then this path will activate. However, if you put something in series, in parallel, if that path is activated, you don't care about the other path. It will go through the other, like the path that is activated. So it is basically gonna desensitize the other path, all right? This is basically what you mentioned is an OR logic. If this one works or the other one works, you're good. That's an OR logic. And by the way, let me go back to my slide. I think I've come a long way. Notice this is AND logic. And when you put things in parallel, that becomes OR logic. Okay, you have options, parallel options. So you're right. To add an extra input, you could just add an extra transistor in series. You see how simple and elegant this thing is, right? Okay, now I'm going to take a step back and let you know that the circuit that I've just showed you, this ones, they are not used in modern digital logic. There are issues. This is a very simple and easy to explain circuit, so I decided to use it. People at some point used to use it, but now we have better solutions. But they are more complicated, as you can imagine, a little bit more complicated. That's why you need 335, 433, right? Okay, but at some point, these were the circuits that people used to use. Anyways, move forward. Number systems. Super simple concept. These are notes for you to read so that you don't have to read a bunch of pages in the textbook just to review, right? You can do that, or you could just go through these quick points. And I'm not going to read all of them. I'm going to go over it on a higher level, and you can read them at home. And if you have questions, you can ask me. So typically, any non-negative integer can serve as the base of a number system. Okay, our generic approach towards number is we always use base 10. That means we have 10 digits. If you have base 4, you'll have 4 digits. If you have base 2, you have 2 digits, right? If you have, say, base 16, you have more than 10 digits, obviously. You have 16 digits. So how do you define the rest of them? Just a quick review. After 9, yes. After 9?
A, B, C.
Yes, you use basically letters like A, B, C, D, E, F. That's all, right? And if you had like some number base, which is like 20, I don't know, you have to come up with more. So my point is, you might be wondering, why would someone randomly choose a number, say 17-based number system, right? There is no reason, obviously. There is logic behind all decisions that we make in engineering. So there is a reason why we choose binary. There is a reason why we often choose hexadecimal. There are some advantages we get in certain algorithms in architecture. Does that make sense? But in digital electronics, as long as digital electronics is concerned, which I'm going to focus on, no matter which number system you use, you eventually convert it into binary. Okay. In other words, we always mention that it's machine language. Machine language is always binary, right? Yes, you code in hexadecimal. You can code in hexadecimal because it is relatively easier for us to handle that way. But deeper down, if you go to the weeds of the hardware, the transistors always get 0 and 1. That's all. Okay. Now, obviously, base 2 is the most important thing for us, but base 10 is what we do in our regular life. I mean, just a quick tangent. You know why universally most people used base 10 numbers. Why didn't people in Europe use base 2? People in US use like say base 16. Why? We always ended up somehow around the world ended up with 10. It's a very interesting, I mean, not my opinion. I read about it. Yes, you're right. He's showing 10 fingers, right? No matter where you are, in Asia, in Europe, in Africa, you always have almost like 10 fingers, right? So people learn counting with their fingers like the babies do, even now. So they say, even my daughter, like she's 2, she can count up to 10. Like, oh yeah, 10. She always stops at 10. She thinks that's where the world ends, right? So like everything, she counts the stair, there are more than 10, but she 10 and she restarts. So that's how, I mean, that tells me, yes, that must have been how people learned to use 10 as a base. Does that make sense, folks? Okay. Anyways, just a quick side note. That's why. Otherwise, there is no other uniqueness in 10 base versus 16 versus 8. Obviously, binary has a unique advantage. It can be represented as high or low, on and off. But people didn't know that until like 100 years ago. And our history goes back like way behind, way before that, right? As you can imagine. Okay, so now this is all covered in what I've just told you. These are some examples. For example, when you have octal number system, you have up to 0 to 7, that means 8 digits, right? I was gonna ask you base 16, obviously 0 to 9, and then A to F. That's how you have 16 base. Let's move to the next one. Conversion. There is an issue with an animation, but it's fine. I want to show you, basically remind you how to quickly convert. And for the most part, typically, there is a strategy that we always use. No matter which base you're using, maybe you are trying to go from base 8 to binary. We always try to use decimal as a common ground, like a base can. We come to decimal, 10 base first, and then go to whatever other base you want to go. Typically, that's the strategy we often use. There are ways to go from A to B directly, but if there is one common way, why don't use that, right? Okay, so this is how we express this. Imagine this is a R-based number, and the position of the number matters. I hope you can see this. 0th position to 1, 2, 3, 4, blah, blah, blah. So this is called the least significant bit to most significant bit. And these numbers, as you see, marked with minus, -1, -2, -3, they represents after the decimal point. Okay, so I think rather than looking at this one, it's easier to look at a direct example. So this is a direct example. This is a binary number, as you see. This is base 2. And you have some digits on the left of the decimal point, some on the right of the decimal point. How can we convert this to decimal, right? Decimal number system. So basically, start from this point, which is the least significant bit. This is the least significant bit, 1. Let me show you. Take the least significant bit. And this is the 0th point. Take the base, which is 2 here, and the power representing the position, which is 0. Now, this is your first step. Second step is take the second digit that you have, which is this, 1. What is the position? First position, right? Because this was 0, so this is 1. So you take, this is your base, 2 raised to 1. Does that make sense, folks? All right. Similarly, 0 is in the third position, which is like 2, basically, because you started with 0. 0, 1, 2. So basically 0 times, this is your base, power, the position. Similarly, finally, this is your fourth digit, which is this one. This is your base. This is the position marker, number 3. If I had more digits, I would have used accordingly. All right. Similarly, move to the other side. These two, which are on the right of the decimal point. What do we have? We have 1 and 1. So we start with one of them, and the position marker would be -1. Then you use the other one, position marker would be -2. Does that make sense? Very quick modification. No, folks, if this were 8 instead of 2, if I mean, I'm just making it up here, okay? If this was 8 base number, what would have changed here? Quickly. Just instead of this, just change them to 8, whatever the base is. This 2 represents the base, right? Does that make sense? And then you end up with the decimal representation. This is a very simple streamlined process. And there are a couple of other examples, as you see. Just go through them if you want to have a quick review. This is an octal number system. This is how you convert it to decimal. Basically, use 8 as base and use the appropriate positions. Similarly, this is a hexadecimal number system. I hope you can still see this. You use 16 as base and then convert the digits accordingly. Okay? Does that make sense, folks? There is a reason why I chose this example. People might wonder, hey, this is a digit in hexadecimal, A, but we don't have any digit like A in decimal. So you just convert it to whatever that means is in decimal. A actually means 10. So you don't just use the digit, you basically use the decimal representation of that digit. Am I making any sense at all? For the other cases, you could just use the digits right away because they are also part of decimal systems. But if there are digits that are not in the decimal system, you convert them like A and F, you convert them automatically into decimal and then multiply them with the base and position. Super simple, quick review. Maybe practice at home. If you have any questions, you can ask me, or you can always quickly review the first chapter of the textbook that we have to basically remind yourself. Obviously, you might be asking, will we ever have to do it? No. You have calculators, you have computers, you have Google. Just ask Google, it will do it for you, right? You don't have to do it anymore. Now, here is why we still care. And before I move on to the next example, next discussion, I want to clarify that. Okay. Have you taken any programming courses? Must have, right? C, I guess, right? Okay. Have you sorted an array? If I give you an array, if I tell you to sort it in a way that you have all the numbers from low to high or high to low, can you do that? Did you see that there are multiple ways to do it? Not just one. There are multiple algorithms. Some of them were more efficient than the others. If you learn just one way, great. But somebody found a different way, and that is more efficient. But we wondered, okay, what is the big deal? The big deal is there will be trillions of sorting operations in big array handling stuff. If you save a microsecond, just take this number. How small is a millisecond? Basically, if something is smaller than millisecond, you don't even register that in your eyes. Does that make sense? We need a millisecond to even sense anything. So if you show me something and take it out within a millisecond, I don't even recognize anything, right? Okay, a millisecond is 10 raised to minus 3. If you have billions of this operation, it's like you see what I'm going with it, right? A million second. It's a long time. So you save a lot of computing, time by making a simple sorting algorithm efficient. Okay, where am I going with this? So if you know how a conversion is made in hardware, in computing hardware, we often have to incorporate dedicated hardware for these conversions, dedicated hardware for adding, dedicated hardware for multiplication and whatnot. If you know the foundational approaches, the mathematical approaches that we use to do something, you could think of ways to connect them with hardware. Otherwise, what you do is you just use whatever is given to you. You never come up with a way to change it. Does that make sense, folks? I don't know how much it makes sense because you're at a very early stage, but this is my attempt to at least give some reasoning behind why we should still care. In the age of ChatGPT, when it can do more complicated stuff, or when we have calculators in our pockets, right? Why should we still care? Because somebody made the circuits inside the calculator and they're improving it. And calculator is just, don't demean that as a simple machine that nobody cares about. As I told you, these calculations in large scale, there is a field called high performance computing. It's not just AI. Trust me, AI is a recent phenomenon, but it has been used for scientific computing. In medical science, when you look for new vaccines, when you look for new medication, by doing chemistry simulation, in our research group, we do some simulations that take more than months to complete. A month to run one simulation, and it felt like, oh man, I used the wrong parameter. Okay, so there goes another month. You see my point? You see where I'm going with it. So one simple efficiency improvement in hardware could change a month to a week. Okay, so, okay, it doesn't mean much. Okay, who cares? During COVID, people cared. Like a month means 10,000 more people did. Like if it takes you a month to develop the medication or vaccine, people will die. So in situations like in actual combat situations, right? You have to make quick decisions. So there, if you don't care about improving the existing hardware, just forget about it. Don't worry about this nitty-gritty. We can just use calculators, right? But if you want to foundationally, basically change the foundational hardware that does this, then we should pay attention. All right. For example, I will teach you, maybe not in this course, in 433, they do a project on it, designing an adder, basically designing an adder circuit for an adder. There is a textbook full of different ways of making adders, right? Ripple carry adder, carry look ahead adder, Manchester adder. So like different types of adders, at least 10, 20 different types of adder circuits. And they're all different from each other because people found a way to basically add two things in different ways. All right, I'm sorry, I don't mean to bore you too much, but I'll try to keep these tangents low. All right, conversion. How do you convert something into binary? Quick recap. Okay, let me show you. So this is a decimal number, 53. You just start dividing with 2 and take the remainder. Does that make sense? So when you divide 53 with 2, you have 26 and remainder is 1 and blah, blah, blah. You just keep doing it until you have 0 left. Your division is basically 0. So then remember, you compiled all the remainders, just put them in reverse order. This is the most significant bit. This is the least significant bit. So 1, 1, 0, 1, 0, 1. That's your binary expression. Simple. Now, if you have, does that make sense, folks? And the example is here for you. You can work it out at home and see whether it really works for you. How do you convert the, fractions? Just take the fraction, multiply it with 2, and you get 1 point something. Take whatever you get after the decimal point, which is always going to be either 1 or 0. Never more than that, okay? When you multiply a fraction, whatever number you get beyond the decimal point is either going to be 1 or 0. So if you get 1, take 1. And this is your first position at a minus 1. And then whatever is remaining, which is 0.25 here, take that and multiply it again with 2. And take whatever you get after the decimal point, which is 0 here, and then take the rest and multiply it again with 2. So here you get 1 after the decimal point. But hold on. Now this one is 0. That means there is no point multiplying it again. You keep getting 0 always, right? So basically, that's where we stop. Otherwise, you could have just had 0, 0, 0, 0. It doesn't mean anything. Does that make sense, folks? All right. Again, you don't ever have to do it manually probably in your lifetime, unless you want to really foundationally change it. But that's the only reason. If you are trying to design hardware which is fully custom made with a technology that is so unique that nobody uses it. If you need some inspiration, this is a tangent note taking. For the longest time, for 60, 70 years, people have been using semiconductors to make chips, as you know, right? Semiconductors and chips are like bound together. They know, oh, we use this technology. In our group and many other groups around the world, people are also exploring an alternative computing platform based on superconductors. How many of you know about superconductors? Some of you have heard about it. You know that they have absolutely zero resistance, and it's not science fiction. They work. And the quantum, you have heard about quantum computers? The quantum qubits are nowadays the IBM and Google, they have superconducting qubits in their quantum computers. So anyways, long story short, we are trying to reimagine the circuits behind logic gate. We are still doing Boolean. We are still doing Boolean logic, but we are reimagining the hardware. And it doesn't look anything like the CMOS. So we had to basically go back and invent how to add. And you'll see a research article from, I can share it with you at some point, published last year, that literally shows how do you design an adder with superconductors. So now we are at a stage where we have to reimagine why semiconductors are having issues. I'm going to get into the details of it. So we have to move away from semiconductors now. You are in all sorts of trouble in your career. Things are changing. It's not trouble, honestly. It's a ripe, I think I would say it's full of opportunities, right? When everything is nice and smooth, they don't need you. Okay, who cares? they're doing their stuff. You just buy from them. But when they're struggling, you have jobs. Okay, come work for us. You have ways to invent. Going back, there is another field called topological electronics. It's 30 years down the line, probably. We are not there yet. Superconductors are already here. Maybe within 5 to 10 years, they will be in mainstream. Okay, but topological electronics, they were discovered recently, topological insulator. And you can make computing systems with them, and there are unique advantages. That means you have to design everything, AND, OR, XOR, whatever, from ground up. So if you don't even remember or know how this nitty-gritty simple computing steps are done, you have no way of reimagining hardware. So every once in a while, when you have to reimagine hardware, you need to go back to the roots. Anyways, so this is another example for you to work on at home. Why is it unique? Why did I choose it? It shows you how to go from a base 4 to base 7. We don't care about either of them. But what I want to show you that you basically first go to decimal, and then from decimal, you convert to binary. That's what I wanted to show you. But if you want to practice at home, the answer is here. Just go for it. Okay. Now, this is a good part for us to stop because we just have 1 minute. We'll talk about Boolean algebra in the next session, in the next class on Monday. All right. Thank you, everybody.